Hi everyone. So today we are learning about hybrid orbitals. So let's first look at why we need to learn about this new theory called hybridization. So we learn about atomic orbitals in previous classes, but with atomic orbitals, we can't explain certain things like real molecular shapes. So for an example, if we look at this methane molecule, which has a tetrahedral shape, the bond angle of hydrogen carbon hydrogen is around 109.5. So if we try to explain this with atomic orbitals, if we look at p orbitals, we know the px, pz and py, these orbitals are 90 degrees apart. So with these, we can't explain this bond angle of 109.5. So that's why we are introducing this new concept called these hybrid orbitals that is able to explain these molecular shapes. So what is hybridization? Hybridization is the mixing of atomic orbitals with similar energies on the same atom to form a new set of orbitals called hybrid orbitals. So here we have these atomic orbitals, they mix, we call it the hybridization to form this new set of orbitals called hybrid orbitals. So these hybrid orbitals, they are different from the original atomic orbitals in energy and shape. So when you have these hybrid orbitals, they can easily bond with other atomic orbitals from other atoms. So it causes effective bonding. So let's look at what are the main features of hybridization. So like I said, hybridization occurs between atomic orbitals with similar energies on the same atom. So the number of hybrid orbitals that are formed is equal to the number of uh, orbitals that are mixed. So for an example here, you have two orbitals mixing and two hybrid orbitals are formed. And this takes place during the bond formation. So these are different types of hybridization. So we have sp and sp2, sp3 and also sp3d. So today we are mainly focusing on these s and p hybridizations. So first, let's look at the easiest one, the sp hybridization. So beryllium chloride, so it's shown here. It's a great example for that. So what happened here is we have one s orbital and one p orbital from the outermost shell. The outermost shell, we call it the valence shell. So from this, that one s and one p orbital mix and hybridize to form this two sp orbitals. So they are oriented 180 degrees apart as shown here. And when this beryllium, when it binds with chlorine, we get a linear molecule. So this sp hybridization results in a linear molecule. So let's try to dig a little deeper into this. So we know the beryllium electron configuration, which is 1s2 and 2s2. So that means in this 2s orbital, beryllium has two electrons, right? But we need to form two bonds in beryllium chloride. So what happens is while electron promotion, that means one of the electron from this s orbital goes to the p orbital. So now we have two half-filled orbitals. So now we can make two bonds, right? So with this is fully filled. So that's why we need this electron electron promotion. And from this, now we have one s and one p, and both are half-filled, and the hybridization happens, and we get two sp orbitals. So we have a s and a p, which is half-filled like this, and we get two sp orbitals like this. They are 180 degrees apart, so it has a linear shape. So now let's look at this sp3 hybridization. This is important because we talked about methane before. So with methane, we see this sp3 hybridization. So it's in the name. So that means in sp3, you have one of the s orbital and three p orbitals are getting mixed or hybridized. So we have one of the s orbital and three p orbitals. These are all from the valence shell. That means the outermost shell, and we get four sp3 orbitals. So they are arranged in a tetrahedral shape. So that's why during the methane formation, we get a tetrahedral molecule. So they have this angle of 109.5. So let's look at how this happens. So you know the carbon electron configuration. So in the outermost shell, that is the valence shell, we have uh, in 2s orbital, we have 2 electrons, and in 2p orbital, we have 2 electrons. But with methane, we need to have 4 bonds, right? So we need like 4 half-filled orbitals. So for this, the electron promotion happens. That means one of the electrons from here go here, and we get this excited state where we have 4 half-filled orbitals. So now the hybridization happens and we get 4sp3 orbitals. So here we have s and 3 p orbitals, which are px, py, and pz, and then we get 4sp3 hybrid orbitals. So they have this structure, like when shown together, it has this tetrahedral shape. So that is the sp3 hybridization. So now let's look at sp2 hybridization. So it's very similar to what we discussed before. So you have one of the s orbitals and 2p orbitals. So here we have one of the s orbital and 2p orbitals hybridized to get sp2 hybridized orbitals. So 3sp2 hybridized orbitals are formed, and these are in 120 degrees apart. It has a trigonal planar shape. So the best example is boron trifluoride. So in boron, this sp2 hybridization happens and it binds with 3 fluorines to make a trigonal planar molecule like this. So these are the other types of hybridizations where a d orbital is being included. So examples are sp3d and sp3d2. So apart from the s and p's, a d atomic orbitals is being involved in this. But we are not going to like talk about this today, but in a next class we will talk about this. And what are these limitations of this hybrid orbital theory? So again, this hybrid orbital theory sometimes cannot explain certain things as well, like the bonding in benzene. So if you look at the benzene, it has this delocalized pi electron clouds like this, but this cannot be explained with hybrid orbital theory. So for that, we need molecular orbital theory again. We'll learn this in a later class. So in summary, so hybridization is the mixing of orbitals that can explain these certain shapes and bond angles, and we have these different types of hybridizations, and it can predict the bonding in simple molecules. So if you have any questions, now we can discuss, and thank you.